Okay, we're picking up with looking at sample space. Remember that we have said sample space is the set of all possible outcomes. And this is the first step in determining probability, is to determine what your sample space is going to be. So that is the first thing that we want to do, is to look at how to find sample space and how to find the outcomes. So just some simple experiments. If we were tossing a coin, our sample space could either be a head or a tail. And of course, if we were doing an experiment and we were tossing it 20 times, then we would toss the coin 20 times and record each toss and what happened for each toss. If we were rolling a die, and remember, if we were rolling 2 die, we would call that dice. There would be 6 outcomes: a 1, a 2, a 3, a 4, a 5, or a 6. We've already talked about those 2 particular types of experiments. But suppose we were using a deck of cards. Some of you have played cards, are familiar with cards. Some of you are not familiar with cards. So let's just talk about what's involved in a deck of cards. First of all, there are 52 cards on a standard deck. Some decks do come with 2 jokers, but we exclude the 2 jokers. So we're talking about a deck of cards without the jokers. There are 4 suits in that deck of cards. There are hearts, spades, and diamonds. For those of you who are not familiar with deck of cards. Uh, if hold on just a moment, folks. All right, sorry for that interruption. All right, we were talking about our deck of cards, the 52 cards with 4 suits, hearts, spades, clubs, diamonds. There's 13 cards in a suit. For those of you that do not know, they go from ace to king. Ace is kind of like the 1. For those of you who play cards, you can play ace high or low. Some people put the ace after the king. Some people use the ace instead of the 1, so that doesn't really matter in what we're doing with probability, whether it's high or low. But there is no 1 card, so some people think of the ace as the 1. So you go 2, 3, 4, 5, 6, 7, 8, 9, 10, and then you have jack, king, and queen. The jack, the queen, and the king are considered face cards. So you'll hear all kinds of terminology used about this deck of cards. You might have a question about the probability of a face card coming up. You might have the probability of one-odd jack. There are only 2 cards in a deck. With one-odd jack. Just so you know that as well. So there's all kinds of questions that come up in terms of deck of cards. So about a deck of cards, you might not know some of that information about a deck of cards. So that just kind of gives you a quick rundown about the outcomes, different kinds of questions that come up about a deck of cards. If you had a bag full of marbles, you would need to know what color marbles are in the bag. So if you had 2 red, 4 blue, and 1 white, then your outcome would be red, red, blue, 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 and white. So again, that is one of the first steps of trying to determine what's going to happen in your experiment, is to determine what your outcomes are going to be. So that is finding your sample space depending on the type of experiment that you have. That's one of the first things that you have to be able to do in terms of probability, is to find that sample space. Now, there is a technique that you can use called a tree diagram. And this is just a technique to help you find the outcomes for sample space. You space by making a list. You can find sample space by using a table. You can find sample space by guessing. You can find sample space by making a table, trial and error. There's lots of ways to find sample space, but we want to try to use a systematic way to help us find the best way, quickest, to determine sample space. So let's take our tossing the coin a step further. Let's say we're tossing the coin 3 times. Not only do we want to look at what happens after tossing it 3 times, but we want to look at the combination of outcomes one after the other. What are the outcomes after tossing it 3 times? So our tree diagram can be used to help us look at the outcomes in succession in terms of what happens. So let's use our tree diagram for the first toss. We toss our coin and we can either get heads or tails. Well, if we toss it again, on the first toss, when we toss it again, we can get heads or tails. And on that first toss, the tails, we can get heads or tails again. So as you notice, the tree is branching as we go. So this was our second toss. And now we're going to toss for the third time. So on that third toss, each of these will branch again. And that's the use of our tree diagram to look at toss 1, toss 2, and toss 3. And now what we're going to do to see what are the possible outcomes is to follow the branches and to connect them. So on the first toss, we got heads, heads, heads. That's a possible outcome. We could have heads, heads, tails. We could have heads, tails, heads. We could have heads, tails, tails. And that's all of the first part. And so now we look at from the tails on the first toss. We have tails, heads, heads. We have tails, heads, tails. We have tails, tails, heads. And we have tails, tails, tails. If we counted up the end branches, there were 8 outcomes. And you'll notice there are 8 outcomes in our list. So not only did the tree diagram tell us how many outcomes were possible, but it also gave us what the outcomes were. So the tree diagram gives us the number of outcomes and what the outcomes are. So the tree diagram gives us 2 bits of information. Not only how many outcomes, but actually what the outcomes are. We could also use a table as a method for finding the number of outcomes as well and what the outcomes are. So we can use a list. We can use a table. We can guess. We can use trial and error. We can use the tree diagram. We can use a technique called combinations. And we can use a technique called permutations. So we've looked at the tree diagrams. We've looked at a list. We did that first. We didn't do a table, but I'll leave that up to you. Guessing is not a very good method, but it is a method. Trial and error is not a very good method, but it is a method. And now we're going to look at doing combinations, and we're going to look at permutations. Another method is also called the fundamental counting method. So all of these are ways of finding the number of outcomes. Any questions so far? Nobody's stopping or saying anything, so I don't want to rush through something that you have a question on. All right, permutation. Actually, let's do combinations first. The order does not matter. You know how we were making our tree diagram and we did heads, heads, tails, and tails, head, tails? The order made a difference in the outcome. When we're doing combination, that order does not make a difference in our outcome. So if we had 5 items, and we wanted to know how many ways we could arrange those 5 items, letters A, B, C, D, and E. Whether it says combinations or it says arrangements. The notations that are used are, it can be written as the number of items combined so many ways. It could be written as C N R, like an ordered pair. And it has a formula. We do N exclamation mark over R exclamation mark N minus R exclamation mark. And for those of you that do not know, that exclamation mark means factorial. If I have 4 factorial, that means I do 4 times 3 times 2 times 1. I do whatever the value is and multiply down to 1 in succession. That's what the factorial means. So 4 times 3 is 12. 12 times 2 is 24. Times 1 is 24. That would be how you would do a factorial. So going back to our problem, how many ways can we arrange 5 items? That would be 5 items combined 5 ways. Or it would be the combination of 5 items 5 ways. In our formula, that means we would have 5 factorial over 5 factorial times 5 minus 5 factorial. Now, for those of you who've purchased your calculators, you should have a combination key on your calculators. The TI-30s have that, or your TI-84 calculators have that. I don't have a TI-30 calculator with me, but you should see this combination key somewhere on your TI-30 calculators. You would need to put in the number first, just like I'm going to do here on this calculator. So I'm wanting 5 items, and then I'm going to press the math key. It's got a glare here. I'm going to go all the way over to the probability. I'm going to go down to choice 3, combination, chosen 5 ways, and press enter to get that result. So that is our answer there. Now, if we wrote this problem, 5 items selected anyway, then we would put in 5. Again, go over to the probability, down to choice 3. Okay. Not getting the answer I thought I was supposed to be getting. I thought I was supposed to be getting 120 here. Okay, I'll have to come back to that problem. Let's do, if we had 8 items, chosen 5 ways, that would be 8 combination 5. In our calculator, that would be putting in the 8 first, math, over to probability and choice 3, 5 ways, and we get 56. Putting that in the formula, that would be the 8 factorial over 5 factorial, 8 minus 5 factorial, and you should still, when you work that out, gotten 56 by hand. As a side note here, you also need to know that 0 factorial equals 1 when you calculate that. Okay, permutation. I'll have to come back to that problem. I don't know why I'm drawing a blank on why it's not working the way I originally worked it. The permutation means that you're finding the number of outcomes, but the order matters. In particular, the permutation is used in problems where you want to find first, second, third, fourth, fifth places. That's a lot of times when you're trying to use a permutation situation, or you're trying to find how many, you have 10 people in a committee and you want to elect president, secretary, vice president. So it's a permutation versus a combination because the order matters. With a permutation, that notation is in permutation R, or P in R. So it looks very similar to the combination. Again, the only difference is the fact that the order matters instead of it doesn't matter. The formula is a little bit different for a permutation. The formula for a permutation is n factorial over n minus r factorial. So it doesn't have that extra r factorial in the denominator when you calculate permutation. An example would be if we wanted to select 6 items in 4 ways. So that means we would have 6 permutation 4. How many combinations would that be? In our formula, that would be 6 factorial over 6 minus 4 factorial. If we were to work that out, that would be 2 factorial in the denominator, which is going to give us 360. On our calculator, similar to combinations, again, those of you with TI-30 calculators, you should have this key as well, the NPR key. You'll punch in the number first, so we're going to do the 6 first. You would press that key first and then the 4. So for us on the TI-84 calculator, we go over to the probability, down to choice 2 this time. with the 4, and we get the 360. Now, these methods are only giving us the number of outcomes. It is not telling us what the outcomes are. It is only telling us the number in our sample space. That is different from our tree diagram, which also gave us what the sample space was. Now, let's look at an example with the fundamental counting principle. This particular kind of problem is used when you might have an example problem that says we have 3 shirts, we have 4 pair of pants, we have 2 ties. How many different outfits can we make with those combinations of clothes? The fundamental counting principle says that we can just multiply to find how many occur. We could make a list or a table and match them up. Shirt 1 with pants 1 with tie 1. Shirt 2 with pants 1 with tie 1. And we could make the list and then count up how many combinations we came up with. That would be very tedious. We could make a chart and organize it and put it all together. But the fundamental counting principle is a quick way to just figure out how many outcomes or how many are in our sample space by multiplying 3 times 4 times 2, and that gives us that our number in the sample space is going to be 24. If we had a small ice cream shop, they had 6 flavors of ice cream. They had 2 cone types. And they had 4 toppings. How many dishes can they make? It would be 6 times 2 times 4, which would be 48 different ice creams. So finding sample space, we looked at the tree diagram, we looked at finding combinations, we looked at finding permutations, and we looked at the fundamental counting principle. All of these are ways to find sample space. Any questions on those? Okay. Now, we're getting into more of the actual probability problems. If we were doing simple probability, for example, if we had a coin toss 100 times, and it landed on heads 44 times. Find the probability of heads. Is this empirical or theoretical probability? Empirical or theoretical? Is it an experiment or is it based on a rule? Are we using actual data or are we using some kind of rule? We are using the rule of probability, but we do that every time. But we're using data based on an experiment, actual data. So it is empirical probability. Now, how do we actually find the probability? We look at how many times did the head occur. It occurred 44 times. What was the total for the probability? It was 100. So 44 out of 100 reduces to 11 over 25. Now we said we can also write a probability as a decimal. So what would that be as a decimal? How would you find the decimal? You would divide 11 by 25 would give us the decimal 0.44. If I needed the percent, what would be the percent for that probability? It would be 44%. You don't have to do that every time. It does depend on the problem. Sometimes it will give you instructions to give the answer as the decimal. Sometimes it will give you instructions to give the answer as a percent. But if it doesn't give you those two particular instructions, you will always give that probability as a fraction in lowest terms. Here's another example of simple probability. We have a drug company testing a new drug. They're testing it on 500 volunteers. 379 observed a weight loss. 62 observed no weight loss. '59 observed an increase in weight? Is this empirical or theoretical probability? Empirical or theoretical? Is it based on experimental data? Is it based on a rule, a theory? What do you think? Anyone?
Experimental.
Yes, it is experimental. You have data that's given to you. It's based on that particular data. We want to find the probability of success of this experiment. So which of this data are we going to focus on? Are we going to focus on the no change? No. Are we going to focus on the increase? No. We're going to focus on the people who had weight loss. So that would be 379 over, what was the total number of participants? The total number of participants was 500. How do I reduce that? Or how do I change that to a decimal? I divide it to change it to a decimal, which would be 0.758. As a percent, that would be 75.8%. So if I wanted to know the success rate for this drug, it had a 75.8% success rate, which is pretty good. Not fantastic, but it is pretty good. Okay, I think we'll stop there. I had some more topics to go over today, but I just don't think we need to rush through them or try to just cram them in. So I think we'll just stop there. Any questions before we finish up today? A lot of terminology that we went over today. What you'll see is some practice problems where you'll practice the permutation calculations, you'll practice the combination calculations, you'll practice the tree diagrams. You will have some questions that will ask you, is it empirical, is it probability? You will have some questions that will ask you to calculate some simple probabilities. So those will be the kinds of questions to expect in your homework practice problems. Any questions there? All right. Have a good day, good weekend. I'll see y'all next week. I'll be traveling this weekend, so I will be pretty tough to get a hold of over the weekend. So if you need something, try to contact me tomorrow, or I probably won't be able to answer you till late Sunday. Okay? All right. See you.